Hello and welcome in video lecture series Demystifying Blockchain. In today's video, we will try to demystify cryptography behind blockchain. In particular, we will see what cryptographic primitives are being used in blockchain. So agenda for today's video is we will see the requirement of integrity and authentication for blockchains. We'll have a look on cryptographic hash functions and digital signatures. Finally, we will have a demo on cryptographic hash functions and digital signatures. So let us get started. Before looking at the requirement of integrity and authentication, we will have to have an overlook of what cryptography is and what are its broader schemes, right? So if we look at the definition of cryptography, it's the mathematical art of secret writing. The main goal of using cryptography is to have a secure communication over insecure channel, right? If we take a simple example, we suppose there are two parties, right? Party A and party B. They want to communicate, right? And this is a channel. They want to communicate with each other. Since this channel is not secure, right? This is insecure channel. Now A wants to send some information, sensitive information to B, right? So A has a message M and he wants to send this message to B. So how cryptography plays role here? A will try to use some cryptographic primitives in order to send this message to B so that he does not have any fear that anybody or attacker, any third party here will be able to see this. So all in all, cryptography allows you to communicate securely, right? Since we know that our communication channel may be wired, it could be wireless. So we have to take care of all the threat vectors, and so threat surface area is huge, right? Whether it is wired or it's wireless channel. Now we will look at broader classification of cryptography schemes, right? And we will see how they allow us to secure our communication. First, if we look at cryptographic schemes at broader level, so we have symmetric key cryptography, also called as secret key cryptography, and we have asymmetric key cryptography. Okay, and this is also called as public key cryptography. First, it was symmetric key cryptography, which was used for a very long time because we were not having some provisions in order that allows us to use cryptography like in asymmetric means. So if we look at symmetric key cryptography, here only one key is being involved. One key is being involved from sender perspective, and the same key is used by the receiver in order to see the actual message. So what is happening in symmetric key is that there is a process going on from sender's side, right? And sender tries to use some mechanism and tries to put key here, right? And he will get output from cryptographic mechanism, right? So this output is not in plain text. This is called as a ciphertext. So what is this process? So basically this is encryption. So if we look at symmetric key encryption, then this encryption scheme could be anything. It's more generic. We can have different encryption mechanism, like we could have AES, DES, or more basic about, you know, polyalphabetic ciphers, monoalphabetic ciphers, Caesar cipher, all kind of stuff. But the fact is, like in case of symmetric key cryptography, we have single key here, right? And the encryption mechanism takes message as input and we get the ciphertext as output. So what is ciphertext now? So we have to take care of all those terms so that we understand how cryptography is being used in blockchain. So ciphertext is unreadable text. You cannot read this, right? This is unreadable, right? If your message is just like hello and you perform some kind of an encryption with symmetric key encryption scheme, and you will get something like this, so that you won't be able to understand this is the message, right? So this is about symmetric encryption. But at the receiver side, the receiver will use decryption and the same key. This key will be again used, and he will use, instead of message here, he will use ciphertext as input in case of decryption, and he will get back as a plain text message. So plain text is the original text, right? So at receiver side, the whole process is reversed, so that he gets the actual message again. So this is about symmetric key encryption. So what is important is to take care that we have, so what is important in symmetric key encryption is that we have a single key that's called as a secret key. So both receiver and the sender are using the same. So sender uses it to encrypt, right? And receiver uses it to decrypt. So now what is the problem? The problem is how to share that secret key, because we have insecure channel, right? So we have to take care of the key itself. So there are multiple ways we could do, right? There are multiple ways of achieving that. Either we could physically go there and just hand over the key written in any form, right, on a plain paper, or something in any form, right? But that's not convenient. So it's considered to be, it was just challenging to use symmetric key encryption before the advent of asymmetric one. So the motivation behind looking into some mechanism that allows us to use two keys, one is public and other is private, is because we don't have that secure channel in order to communicate that secret key. So we will look at asymmetric key encryption scheme now, asymmetric key cryptography in general sense. In asymmetric key cryptography or public key cryptography, we have two keys. One is called as public key, other is called as private key. As the name suggests, this is made available to public, right? This is public and this has to be kept secret. So this is private key, and this is private to the one who is intending to use this kind of encryption scheme, right? So how is it different from symmetric key encryption? It is different because we don't need to communicate our private key to other parties, right? What will happen here, if we look at simple example that A wants to transmit message M to B, again the simple example here, this is A, he wants to send something to B. Now what will A do? A will simply use, if B intends to receive some message M, right, from A, so B will create two keys. One is public key, another is private key. Okay, so this public key is available to public, and he will give this public key to A. What A will use any form of asymmetric encryption scheme. It could be RSA, it could be elliptic curve cryptography. We will come to these concepts later when we see in actual sense how Bitcoin works and how cryptography works there. So here the motive is to have a template kind of a structure where we look what crypto primitives are being used, right? So this is again encryption here. So the input M is to encryption scheme, and the key, which key will be used here? It is the public key. Whose public key? It is B's public key, right? Public key of B. And the output will be ciphertext, that that this is unreadable text. This is ciphertext. Now this ciphertext goes to receiver B. Okay, B will use again decryption, which key he will use? He has to use his own private key of B, and uses the ciphertext as well that he receives. Since since this ciphertext is not in readable format, so you need not to worry about who will get this in between of the channel, right? So the output of the decryption is again the plain text message, that is message M. So this has removed that problem of communicating that secret key over an insecure channel. So this has revolutionized the way we communicate over the internet, and this is the scheme mostly we use to share the key first, then we can use symmetric key as well for rest of the stuff, right? So this has revolutionized the way we communicate over the internet in particular, right? So this is the general sense, the general introduction to cryptography and two broader schemes in encryptions, right? In encryption, two broader definitions of so this is brief introduction about cryptography, and it is broader classification in terms of encryption schemes. We have seen symmetric key encryption, we have seen asymmetric key encryption. So we know that asymmetric key has revolutionized the way we communicate. Now we will look into other requirements. Okay, so now we will look on other requirements. The first one is integrity. Before defining integrity, we have seen two different types of cryptographic schemes. One is asymmetric and symmetric. So that was being done with the help of what scheme? Encryption scheme. So encryption is basically used to guarantee about confidentiality security service. What is confidentiality? If you have a sensitive data, suppose any message M, you don't want any unintended party to have that data, right? So you want to prevent that from anyone else to have a look on that. That is related to the privacy. So confidentiality guarantees that your data will not be seen by any unintended party except the one whom you wish. Suppose you want to send it to B. B is the only one who will be able to get that data and see the actual message. So which security service is being used to guarantee confidentiality? Confidentiality is being guaranteed with the help of encryption. Now we will look at the integrity. So where comes this integrity, right? We have seen a simple example, right? We have seen a simple example where A tries to send some data to B, and we have guaranteed that M will be only viewed by B. So this was about confidentiality. Now what about the contents in M, right? The contents in M are not being altered or modified during the transit or during at rest or any storage. Maybe M is being stored in anywhere in between the channel. So how you can guarantee about the integrity of M, right? So integrity is the security service that guarantees that M is not being altered or modified in transition or at rest, right? So which security scheme is being used? So this is security, right? Service integrity. But which cryptographic primitive is being used to guarantee integrity? It is the cryptographic hash functions, right? So first we will look at the definition of integrity, then we will look at which crypto primitive is being used to guarantee about integrity, right? So as already defined, it ensures that data that is being transmitted, that is being shared or communicated over the insecure channel is not being altered during on at rest or during transmission, right? So integrity is a security service which is being guaranteed through or which is being achieved with the help of cryptographic hash. So we will have a broad overview of what are cryptographic hash, what are cryptographic hash functions, and what are their properties, right? So if you look at a diagram, it's a mathematical function that takes a variable size input and produces a fixed size value called as hash value. So we'll look at some of the properties of hash functions. So it should be very easy for us to calculate the hash of any given message. But before that, we say this is basically a mathematical function, right? One-way function. You imagine there is a mathematical function, right, that takes a variable size input and it produces a fixed size output called as hash value, right? So this is only one way, that is, it is easy to compute hash of any given message, right? But it is computationally infeasible to go back to x from h, right? I hope this makes sense now, right? Okay, so we'll move forward and look at other properties. Okay, so we have seen it is very easy for us to it should be easy to compute hash of any given message. It should be deterministic, that is, every time you try to calculate the hash value of any given message, just like say x or y, right? If first time you try to compute the hash of x, it gives one value, and again if you try to compute the hash of again the same message, this x, you will get the same value. So this is deterministic, means if you try to calculate hash of any given message and you repeatedly do the same for the same message, you will get the same hash value, right? Third point, so it's not inevitable, that I already explained. This is a one-way mathematical function. So from message to hash, you will be able to go through, right? And it's easy to compute that, but you will not be able to get back from hash to message. So that's why this is non-invertible. That is, given the hash, you cannot discover what input it was, right? Yeah, right. Now about the uniform distribution property of hash functions, it's like there is equal property of equal probability of hash value is same for any other message, right? So simple is like, if we try to take an example for this. So this is our hash, just for the example of hash value, right? And we are calculating hash of messages, and if we calculate one hash and it goes to here, and next time the probability of hash value is like it can go to some other place. Okay, so all in all, we can say it's collision resistant. It is like, if we look at the other property, collision resistance, that will make more sense. It is like infeasible to find two different inputs that yield the same hash. What does that mean? That is, if we have inputs x1, and we calculate the hash of this x1, right, and we get h1. Now these two messages are different, right? So it is almost computationally infeasible for you to get this scenario. That is, you have two different messages, x1 and x2, and we have only one value of hash taking the hash of these two. So it is infeasible to find two different inputs that yield the same hash. So what is the ideal scenario here? You will get different hash if they are x1 and x2 are different. If they are same, then definitely this is deterministic, you will get the same hash value. So these are like some basic properties of hash functions. So all in all, what hash function does, it takes variable size input. Okay, if you look at here, it takes variable size input and you feed into this hash function. This could be any hash function. There are multiple hash functions: md4, md5, SHA1, SHA2, SHA256, SHA256, KCAC256. These are all different variants of the functions. How they are different? They are different in the mechanism they use, just like doing some operations of XOR and some other operations like shift, right shift, left shift, and what is the size of their output, right? If we take a simple example of SHA256, okay, so why this is called as secure hash algorithm 256, because it produces hash value of 256 bits in length, right? So this is the hash scheme that is being used in most of the blockchain platforms. If we take an example of Bitcoin, we take example of Ethereum. In Ethereum, we use kcac 256, that also produces 256 bits, right? So also there is let me just rub this. One more property, and that is important. It is infeasible to modify message without changing hash. Again, if you have a message m and we get a hash value h1 if we take a hash of m, but it is infeasible if we try to modify message m to m dash and the hash remains same. Soon we try to change, even a minor modification of a dot or any comma behind the message, it will produce a different hash, right? So this is like it's practically infeasible to modify message without changing the hash. So that is, again, this ensures about the collision resistance. If it would have been a case, that could have been a collision. So since the hash functions are collision resistant, soon we try to modify the message, we get a different hash value. All right. Now, after looking at the requirement of integrity, we will go to authentication. First, we have seen about confidentiality, and that was guaranteed by encryption. Then we have talked about integrity, that was guaranteed by cryptographic hash functions. Now we will look at authentication. So what is authentication, right? We will look at the definition. It is used to make sure that you really communicate with the partner you want to, right? So how you could ensure that? So it's about guaranteeing that you are communicating to the intended participant, right? And if someone claims that he is A, so authentication guarantees that it actually is A, right? So this allows us to identify the identity of a person, right? So it uses to make sure that you really communicate to a participant which he claims to be, right? So what cryptographic scheme is used to guarantee authentication or used to achieve the authentication? It is digital signature. So what is digital signature? It's again a mathematical scheme for demonstrating two things: authenticity as well as integrity of digital message or documents, right? Okay, so we will look at how digital signatures work, but it's just a combination of encryption and hash, right? We first do hash, then we do encryption, and that's what helps us to achieve and generate the signature. Then we will also look at an example where we try to generate digital signature and also try to verify the digital signature. So basically digital signatures are used to guarantee two things, right? Authenticity as well as integrity, right? So authenticity is like simply you are 100% sure that the participant is the actual one whom what he claims to be, and you are satisfied that you are communicating with the real entities, right, with the help of authentication. Okay, let us look at a simple process of signature generation and signature verification. If you look at here in signature generation process, if sender A has some message to transfer, right? First we have seen if we want to have a confidentiality, we use encryption. Now we want to have both integrity as well as authentication, then we have to use digital signatures. So first, this A has message M. It could be simple message, it could be transaction data if we talk in blockchain sense. Then we just try to use any hash function. It could be SHA-256, right? And we feed this message M here and get the hash value, right? Once we get the hash value, so if it is hash value, then we use encryption mechanism, right? But you have to take care here, very important concept. Now we have seen that the encryption is usually done with the help of receiver's public key, but in case of signature we use sender's private key, that is the private key of A is used in encryption here. So if we have hash value, right, we use encryption and we use sender's private key, that is private key of A, and we get, this is hash value, we get a signature. So that is here. So we get the signature out of this. But the important concept here is encryption is being used, but we do encryption with sender's private key. Who is the sender here? It's A here. So we use A's private key in order to sign the hash value of the message, and we get the signature, right? And we send the actual data as well as the signature to receiver. Okay. When receiver receives this, what he receives, it is the message as well as the signature. What he does, he will also try to calculate the hash value of that data, right? Using the same very hash function, that is SHA-256. Okay. And since he also has this signature, right, he will use the decryption method. But which key he will use? He has to use sender's public key, right? Since public key is public to everyone, right? Public to one who is interested in the communication. He will use sender's public key here. So since we have seen encryption does what? It just encrypts this H value, right? And gets the signature. If we reverse this process, we use decryption, and decryption will use what? Decryption will use signature as well as the key. But which key? Sender's public key. And once the decryption is successful, you will get the hash value H, right? So from receiver gets two hash values now. One from the simply taking hash of the message, plain message, and from the signature. Now he compares those two hash values. If they are equal, the signature is valid. If they are not equal, signature is invalid, right? So what it guarantees two things: authentication, that it was really A who has signed, because the receiver was able to decrypt with A's public key. That guarantees about authentication of A, as he is the actual signer of the message, because we were able to decrypt with his public key, right? This public key, sender's public key here. Okay. Other thing also, we have confirmed that the message has not been altered. Why? Because we have taken the hash value, and the hash value is the same hash value that was being sent through signature, right? Because we get the same hash value from here. So you have seen, with the help of digital signatures, we were able to verify two things. One, we were guaranteed that it was the message signed by A, and the message was not being altered. Now I will just take a simple example for understanding. If we see, you have some fiat currency. Let us take, you have 500 rupees note, or $1 note, any example you can take. When you go to a grocery store, you try to buy some grocery. What it guarantees, since you have $500 or 500 rupees note or $1 note, it guarantees that you are the owner of that 500 rupees or $1 note, and you have the power to spend it, right? How you could do the same thing in blockchain? If you take an example of cryptocurrency on blockchain, you should be able to verify that you are the real owner and you have the authority to spend it, right? So these are the concepts of cryptographic concepts that helps you to achieve this. With the help of digital signatures, you will be showing that you have the power to spend and you are the real owner. If you produce the signature, you will show to the nodes on the network that you are the real owner of that transaction, right? Of that coin, if we take an example of Bitcoin. So this is the power of cryptography. It allows you to show them that the transaction has not been altered and you are the real owner of the transaction and you have the power of that transaction. So what is beautiful here in blockchain is that in case of Bitcoin, you can just prove that all sort of, like, right from the source to destination, you can prove who has owned that Bitcoin which you should try to spend, right? But in case of fiat currency system, you cannot prove, there is no way to prove that you have bought that 500 rupees note legally or illegally, right? But in case of Bitcoin, you can show the proper, like, route from the source to destination. First, where this transaction comes in, to whom it goes, then to whom it goes, finally it has reached to you. Now you have the ability to spend it. So you can see all sort of things there, right? Okay, so we have seen this digital signature kind of concept. It guarantees two things here. It guarantees integrity as well as authentication, right? So mostly if you see in blockchain platforms, these are the two concepts that are being used here, right? So encryption is being used, but as part of the signature. Okay, now we will look at some properties of these digital signatures. Signature must be bit patterns that depends upon the message being signed. Yes, this is true. If we look at example here, signature is being generated from what? From message. If you try to modify message, you will get different signature. So this property is being satisfied here. Other property is it must be signature must use some unique information to the sender. If we look at again in this example signature generation, we are using something that is unique to the sender. If you recall, we are using private key of sender, so that is unique to sender, right? So this claim is also we are satisfying. Other thing is that it is impossible to forge a digital signature. Yes, because if you try to, if someone gets this signature and tries to modify it, right, but he will not be able to sign it because he does not have access to this private key. Okay, right? He does not have access to the private key, so he will not be able to produce the signature. He will forge it, but that will be invalid here because it will not result in the same hash. Okay, non-repudiation. What is non-repudiation? It is a security service, right? That is like if someone has participated in communication, he will not be able to deny that, right? Simple example for this, if I receive a mail from your email address, then you cannot deny that you have not done that. So how that is being guaranteed is because we know the password for your email is with you and that is unique to you. In the same case here, if we see the private key is with you, if you receive a signature from your side, you cannot deny that you have not signed it, right? So now we have seen the third property is also being guaranteed here: integrity, authentication, and non-repudiation. Okay, right? So these are like basic procedures, cryptographic things. In very general sense, we have talked about them. But when we take the example of Bitcoin, we will see more. We'll dig deep into it, right? We will see how ECDSA is being used as a signature scheme, how SHA-256 is being used. We will have a look on that in Bitcoin, and then we will go to the Ethereum and see how these concepts are being used there. Now is the time to have a demo. Okay, so let us take a look at hash functions. So I already explained this is a one-way mathematical function that takes variable size input. Let us take a simple example here. If we take an input of hello, you get a different hash. Since we are using SHA-256, you will get 256 bits here, right? Every character represented by 4 bits. If you just count those and multiply with the 4 bits, you will get 256. So hello results in this hash. Okay, if you just try to modify this hello by simple dot, okay, you will get a completely different hash. This is called as avalanche effect. That is, a very small change in input results in a drastic change in the output. Okay, I hope this makes sense now. So this hash function is being used in most of the blockchain platforms, including Bitcoin. So see, if we try to hash the hello, it will be again, no matter how many times you try to hash this hello, the hash value will be the same. So that is the property of this deterministic property. If you try to do small modification, you will get another thing. There will be no two different messages that will result in the same hash. That is, they are collision resistant. Okay, so this is about hash functions. Now let us take a look at digital signatures. For understanding digital signatures, we have to first understand the public private key, right? So this will make more sense when we will take example of Bitcoin, and we will go into deep details when we start the Bitcoin series. Here you have to understand the private key is simply a random number, and there is an algorithm that takes this private key and computes public key corresponding to this private key, right? So you assume private key is a random, right? So if I hit random button here, you get this, and correspondingly you get the public key. So there is a mathematical relationship between private and public key here. So whatever private key you generate first, it will give result to you. It will give the public key, right? If I try to hit random again, so you will get the public key again. Now, why we use this? Because we have seen in signature scheme, we do encryption with the help of sender's private key. So we have to use this private key. Where we will require this public key? In case of signature verification. Let's do that. We will go to the signatures. So we have specific message hello. Okay. We use private key to sign. But internally, what is being done first? Hello is being converted into what? Hash function. Hash function. It is fed to the hash function and we get the hash value. Then we use this private key to sign that. If we try to sign, we will get the message signature. Here is our message signature. Okay. So it depends upon the unique information that is using. Whose private key is this? It is sender's private key. Now if you want to verify, which key you will use? You have to use sender's public key to verify, and two things you require: message, what? Message signature, and the public key. If you see, message, public key, and the signature we use. Since these are the same, we have not altered. If we hit verify, you will be able to successfully verify this. Here we go. Right. So if I try to modify the signature, right, in between here, you will see, and try to verify, you won't be able to verify it, just because this signature is not being signed by the actual private key, since we modified it here, right? So this guarantees about the authentication, since only the real owner of the private key will be able to generate the signatures corresponding to his private key. Okay. Now if you try to even change, like if you go back and verify, it is fine again. If you try to modify message, you will say with a single dot even, and try to verify, still you will not be able to verify, just because this will guarantee about the integrity of message now, right? Hit the verify, still not. If you just remove this dot and hit verify, you are good to go, and your signature is being appropriately verified, and your transaction will be accepted in blockchain system. So these things help us, these are very important concepts. First, cryptographic hash functions and digital signatures. Most of the times in blockchain, you will see these two concepts, these two cryptographic concepts. So this is it for this video. If you like the content, hit the like button of the YouTube video and do subscribe the channel, Learn to Apply. Thank you.